Welcome to this coding walkthrough. Today, we'll tackle the popular problem number 70, climbing stairs. This is a classic dynamic programming challenge where we explore how to calculate the number of distinct ways to climb a staircase, given that you can take either one or two steps at a time. Let's dive in and explore different approaches to solve this problem effectively. In this problem, we are tasked with figuring out how many distinct ways you can climb a staircase that has n steps. The key here is that each time you make progress, you can either climb one step or two steps. So, the challenge is to determine the total number of unique combinations of one-step and two-step moves that would allow you to reach the top of the staircase. For the input, you are given an integer n, which represents the total number of steps in the staircase. The value of n will always be between 1 and 45. The output will be another integer, which represents the total number of distinct ways you can climb to the top of the staircase. Let's look at some examples to understand this better. If n is 2, the output is 2, because there are two ways to climb to the top, either by taking two one-step moves, or by taking one two-step move. Now let's explore more examples to build on this idea. When n is 3, the output is 3, because there are three distinct ways to climb to the top. The first way is to take three individual one-step moves. The second way is to take one one-step move and then one two-step move. And the third way is to start with a two-step move and then take a one-step move. This illustrates how the number of ways increases as n gets larger, because you have more combinations of one-step and two-step moves available to you. These combinations are what we need to calculate for any given value of n. Let's now take a look at another example where n is 4. To see how the number of distinct ways continues to grow. For n equal to 4, the output is 5, because there are 5 distinct ways to climb the staircase. The first way is by taking 4 individual one-step moves. The second way is to take two one-step moves followed by one two-step move. The third way is to take one one-step move, then a two-step move, and then another one-step move. The fourth way is to take a two-step move followed by two one-step moves. Finally, the fifth way is to take two two-step moves. As you can see, the number of combinations grows because there are more possible arrangements of one-step and two-step moves as n increases. However, the problem has constraints to ensure that n is always between 1 and 45, and the result will fit within a 32-bit signed integer. Let's also discuss some edge cases that you should consider when solving this problem. For edge cases, consider the smallest input, where n is 1. In this case, there is only one way to climb the stairs, which is by taking a single one-step move. For n equal to 2, as we discussed earlier, there are exactly two ways to climb the stairs, either two one-step moves, or one two-step move. On the other hand, for larger values of n, such as 45, the number of distinct ways can be quite large, but it will always fit within a 32-bit signed integer. This means that your solution needs to be efficient enough to handle both small inputs, like n equals 1 or 2, and large inputs, like n equals 45. By carefully considering these constraints and edge cases, you can ensure your solution will work correctly for all valid inputs. To solve the climbing stairs problem, we need to calculate the number of distinct ways to climb a staircase with n steps, where each step allows either one or two jumps. One approach to consider is the brute force method, which uses a recursive tree to explore all possible combinations of steps. The intuition here is to treat the problem like a decision tree. At each step, we either climb one step or two steps, and we continue this process recursively until we reach or exceed the target. The algorithm involves recursively calculating the number of ways to climb the remaining steps, combining the results for n1 and n2. However, this approach has a major drawback: it's highly inefficient. With a time complexity of O2 to the power of n, each step spawns two recursive calls, leading to exponential growth. Additionally, the space complexity is O(n) due to the maximum recursion depth. This inefficiency arises from repeated calculations of overlapping subproblems, making it impractical for larger inputs. To address the inefficiency of brute force recursion, we can use memoization, which is a top-down dynamic programming approach. The idea here is to cache the results of previously solved subproblems so that we don't recompute them. The algorithm is similar to brute force, but before solving each subproblem, we check if the result is already stored in the cache. If it is, we reuse it, otherwise, we compute and store it for future use. This optimization reduces the time complexity significantly to O(n), as each subproblem is solved only once. However, it still has a space complexity of O(n), due to the cache storage and the recursion stack. Another approach is tabulation, which is a bottom-up dynamic programming method. Instead of recursion, we build the solution iteratively starting from the base cases. We define an array dp where dp, I, represents the number of ways to climb I steps. Starting with dp, 0 equals 1 and dp, 1 equals 1, we compute each subsequent value as the sum of the previous two, dp, I, equals dp, I1, plus dp, I2. This method also has a time complexity of O(n), but it uses O(n) space due to the dp array. While this is more efficient than recursion, the space usage can still be optimized further. The space optimization approach builds on the tabulation method by recognizing that we don't need to store the entire dp array. To compute dp, I, only the last two values, dp, I1, and dp, I2, are required. This allows us to reduce the space usage to O(1) by using just two variables. The algorithm begins by initializing two variables, previous 1 and previous 2, to represent dp1 and dp0, both set to 1. Then, for each step from 2 to n, we calculate the next value as the sum of previous 1 and previous 2. After calculating the next value, we update the variables to reflect the new state. Previous 2 takes the value of previous 1, and previous 1 becomes the newly calculated value. This approach retains the time complexity of O(n), while minimizing space usage, making it the most efficient solution. By eliminating the need for recursion and reducing memory overhead, this method is particularly well suited for scenarios with large input values. The chosen strategy for solving this problem is the space optimization approach. It combines the efficiency of dynamic programming with minimal memory usage. The key insight lies in recognizing that the problem is essentially about calculating Fibonacci numbers, as each step depends only on the previous two steps. This allows us to achieve O(n) time complexity and O(1) space complexity, making it the optimal solution for large inputs. In comparison, the brute force approach is far too slow for larger inputs due to its exponential time complexity. Memoization improves the time complexity but still requires O(n) space for caching results. Tabulation is simpler than memoization but still uses extra space unnecessarily. The space-optimized approach strikes the perfect balance between simplicity and efficiency, making it the best choice for solving the climbing stairs problem in a practical and scalable way. The climbing stairs problem asks us to determine how many distinct ways there are to climb a staircase with n steps, where you can climb either 1 or 2 steps at a time. This is a classic combinatorial problem that can be addressed efficiently using dynamic programming. To solve it, we start by defining a recurrence relation for the problem. The total number of ways to climb n steps, represented as f of n, can be broken down into two scenarios, climbing 1 step from n1, or climbing 2 steps from n2. This gives us the relation f of n equals f of n1 plus f of n2. We also have two base cases, f of 0 equals 1, as there is only one way to stay at the ground, and f of 1 equals 1, as there is only one way to climb the first step. This recurrence forms the foundation of our approach. Now, to solve the problem efficiently, we choose dynamic programming as our approach. Dynamic programming is ideal here because the problem has overlapping subproblems. For example, calculating f of 5 requires f of 4 and f of 3, but f of 4 also requires f of 3 and f of 2. Without optimization, a naive recursive solution would repeatedly recalculate the same values, leading to exponential time complexity. By storing intermediate results, dynamic programming eliminates redundant computations and reduces the time complexity to O of n. To implement this, we create an array, dp, of size n plus 1 to store solutions for all subproblems from 0 to n. We initialize the base cases, dp of 0 equals 1 and dp of 1 equals 1. Then, we use a loop to fill the dp array from index 2 to n, where dp of I is computed as dp of I1 plus dp of I2. This guarantees each subproblem is solved only once, and its result is reused. Once the dp array is fully populated, the solution to our problem is stored in dp of n, which represents the total number of ways to climb n steps. Additionally, there are a few key insights worth noting. First, the recurrence relation mirrors the Fibonacci sequence, meaning f of n corresponds to the n plus 1th Fibonacci number. Recognizing this connection allows for further optimization. For example, instead of storing the entire DP array, we can maintain only the last two computed values, significantly reducing space complexity from O of n to O of 1. This space-efficient approach relies on updating two variables as we iterate through the steps. Finally, we must handle edge cases where n is 0, 1, or 2. For n equals 0, there's only one way to climb no steps. For n equals 1, there's only one way to climb a single step. And for n equals 2, there are two ways, one step plus one step, or a single jump of two steps. Analyzing the complexity, the time complexity of this approach is O of n because we compute each step from 2 to n exactly once, and each computation is constant time. For space, if we store the entire DP array, the complexity is O of n. However, with the space optimization where we retain only the last two values, the space complexity is reduced to O of 1. Let's walk through an example with n equals 5. We initialize the DP array with base cases, dp of 0 and dp of 1 are both 1. Next, we compute dp of 2 as dp of 1 plus dp of 0, which equals 2. Then dp of 3 is dp of 2 plus dp of 1, giving us 3. Similarly, dp of 4 is calculated as dp of 3 plus dp of 2, resulting in 5. Finally, dp of 5 is dp of 4 plus dp of 3, which equals 8. Thus, the total number of ways to climb 5 steps is 8, and this value is returned as the result. Alternatively, we can use the space-optimized method to achieve the same result with fewer resources. Here, we initialize two variables, previous equals 1 and cur equals 1, representing the base cases. For I equals 2, we update cur to previous plus cur, which is 1 plus 1, resulting in 2, and then set previous to the old value of cur. For I equals 3, cur becomes previous plus cur, now 1 plus 2, which equals 3, and previous is updated to 2. Repeating this process for I equals 4 and I equals 5, we calculate the values 5 and 8, respectively. By the end, cur holds the total number of ways to climb 5 steps, which is 8. This approach demonstrates how we can achieve the same result with only constant space, making it an elegant and efficient solution. The problem climbing stairs is solved using a dynamic programming approach with space optimization. The goal is to calculate the number of distinct ways to climb a staircase with n steps, where you can climb either 1 or 2 steps at a time. The solution begins by handling the base cases. If n is 1 or 2, the number of ways to climb the stairs is equal to n itself. This is because for one step, there is only one way, 1. For 2 steps, there are 2 ways, 1 plus 1 or 2. For cases where n is greater than 2, the solution uses a dynamic programming approach. The idea is based on the recurrence relation. F n equals f n1 plus f n2. This means that to reach the nth step, you can either come from the n1th step or the n2th step. The number of ways to reach these 2 steps is already calculated. The algorithm initializes 2 variables, first and second, to represent the number of ways to climb 1 and 2 steps, respectively. Then, it iteratively computes the number of ways to climb up to the nth step. For each iteration, 1. Compute the current step's ways as the sum of first and second. 2. Update first to hold the value of second, for the next iteration. 3. Update second to hold the value of the current step. By the end of the loop, second holds the total number of ways to climb n steps. This approach is very efficient, with a time complexity of O(n) and a space complexity of O(1), as it only uses 2 variables regardless of the input size. This concise yet efficient solution ensures optimal performance, making it suitable for constraints up to n equals 10 to the power of 4 as typically required in competitive programming. This is the Java implementation of LeetCode problem number 70, climbing stairs. The logic mirrors the Python implementation provided, using a bottom-up approach with 2 variables to track the number of ways to climb stairs. The primary difference lies in Java's explicit type declarations and the absence of Python's dynamic typing. The solution is efficient, operating with O(n) time complexity and O(1) space complexity. To solve the problem with an input of n equals 3, we aim to find the number of distinct ways to climb 3 steps. The approach we use here follows a Fibonacci-like sequence. First, we initialize our base cases. If n is less than or equal to 2, we can simply return n, as there are n ways to climb those steps. However, since n is 3, we proceed. We initialize two variables, first is 1, representing the number of ways to climb one step, and second is 2, representing the number of ways to climb two steps. Next, we iterate from step 3 up to n, inclusive. For step 3, we calculate current as the sum of first and second, which gives us 3. This represents the number of ways to reach the third step. We then update first to the value of second, making it 2, and second to the value of current, making it 3. Finally, after the loop completes, the value of second holds our result, which is 3. This tells us there are 3 distinct ways to climb 3 steps. Now we calculate the number of distinct ways to climb 5 steps. Again, we start by initializing our base cases. If n is less than or equal to 2, we return n, but since n is 5, we proceed. We set first to 1 and second to 2. The iteration begins at step 3 and continues up to step 5. For step 3, we calculate current as the sum of first and second, which is 1 plus 2, resulting in 3. We then update first to 2 and second to 3. Moving to step 4, we calculate current as 2 plus 3, giving us 5. We update first to 3 and second to 5. Finally, for step 5, current is calculated as 3 plus 5, which equals 8. We update first to 5 and second to 8. These calculations give us the number of ways to climb each step incrementally. After finishing the iteration, the value of second now holds the final result. For n equals 5, second is 8, meaning there are 8 distinct ways to climb 5 steps. Let's now explore the solution for n equals 6. Similar to before, we start with the initialization step. If n is less than or equal to 2, we return n, but since n is 6, we proceed. We set first to 1 and second to 2. These represent the ways to climb 1 and 2 steps respectively. In the iteration step, we calculate the number of ways to climb from step 3 to step 6. For step 3, current is calculated as 1 plus 2, resulting in 3. We update first to 2 and second to 3. For step 4, current becomes 2 plus 3, giving us 5. We then update first to 3 and second to 5. For step 5, we calculate current as 3 plus 5, which equals 8. We update first to 5 and second to 8. Finally, for step 6, current is 5 plus 8, resulting in 13. We update first to 8 and second to 13. After the loop, second holds the result. For n equals 6, there are 13 distinct ways to climb the steps. This demonstrates how the Fibonacci-like approach effectively provides the solution for any given n. The time complexity of this solution is O, n, and here's why. The algorithm uses a single loop to calculate the number of ways to climb the stairs from step 3 up to step n. First, we initialize two variables, first and second, which takes constant time, or O1. Then, the loop runs exactly n2 times, from step 3 to step n. Each iteration of this loop performs a constant amount of work, one addition operation to calculate the current number of ways and two simple variable assignments to update first and second. Since each iteration takes O1 time, the total contribution from the loop is O(n)(2), which simplifies to O(n). Combining this with the O1 from initialization, the overall time complexity is O(n). The space complexity of this algorithm is O1, meaning it uses a constant amount of extra memory regardless of the input size n. To understand this, consider the memory usage of the algorithm. It defines three scalar variables, first, second, and current, all of which require a fixed amount of space. There are no recursive calls that would require a call stack, nor are there additional data structures like arrays being allocated. This distinguishes it from other approaches, such as recursion or dynamic programming using arrays, which would consume memory proportional to the input size. By updating the variables in place and avoiding any extra memory allocation, the algorithm achieves a space complexity of O1. Let's compare this approach with other common methods. A brute force or naive solution would rely on recursion, where the function climb stairs, n, would repeatedly call itself for n1 and n2. While this approach is conceptually simple, it has exponential time complexity, 2 to the power of n, due to redundant calculations. Additionally, its space complexity is n, as the maximum depth of the recursive call stack depends on n. Another alternative is dynamic programming with arrays. This method improves the time complexity to n by storing intermediate results in an array, avoiding redundant calculations. However, it has a space complexity of n, because the array size grows with the input size. The current solution, on the other hand, achieves optimal performance by using only two variables to store the last two results. This reduces the space complexity from n to 1, while maintaining the time complexity at n. For this problem, the time complexity remains n across all scenarios: best, average, and worst case. This is because the algorithm always loops from step 3 up to step n, regardless of the specific input value. Similarly, the space complexity is always 1, as the algorithm consistently uses a fixed amount of memory that does not depend on the size of n. To provide a mathematical justification for the time complexity, consider the amount of work performed in the loop. Each iteration executes a constant amount of operations, 1, and there are, n2, iterations. Multiplying the number of iterations by the work per iteration gives us, n2, *, 1, which simplifies to n. When we include the constant time 1 initialization step, the total time complexity remains n. This consistency across all scenarios highlights the efficiency of the algorithm. When solving the climbing stairs problem, there are a few common mistakes to watch out for. First, some people confuse this problem with the Fibonacci sequence. While the recurrence relation is similar, the base cases are different. For Fibonacci, f(1) equals 1 and f(2) equals 1. However, in climbing stairs, f(1) equals 1, but f(2) equals 2, because there are two distinct ways to climb two steps. Another mistake is using plain recursion without memoization. This results in exponential time complexity, 2 to the power of n, because the same subproblems are calculated repeatedly. To avoid this inefficiency, memoization or a bottom-up dynamic programming approach should be used, both of which reduce the time complexity to n. Lastly, edge cases should not be ignored. For instance, when n equals 0, the answer should be 1, representing the one way to do nothing. Failing to handle such cases can lead to incorrect results or even runtime errors, especially for large inputs near the problem's constraints. Another common mistake is overcomplicating the solution. Some may try to implement advanced techniques like matrix exponentiation, which provides an log n time complexity. However, this is rarely required unless specifically asked. A simpler dynamic programming approach is easier to implement and debug while still being efficient. Additionally, incorrect space optimization is another pitfall. While reducing space usage to just two variables is a great optimization, mishandling the updates to these rolling variables can lead to errors. It's critical to carefully track and update the variables in the correct order to ensure the solution remains accurate. During interviews, there are several key insights to focus on when discussing the climbing stairs problem. Start by clearly explaining the recurrence relation, fn equals fn1 plus fn2, which arises from the two choices at each step, taking one step or two steps. Be prepared to discuss the trade-offs between recursive approaches with memoization and iterative dynamic programming. While both achieve n time complexity, iterative DP is often preferred due to lower overhead. If you implement the space-optimized solution using two variables, highlight how it reduces memory usage while maintaining correctness. Always address edge cases like n equals 0 or n equals 1, as well as large inputs, to demonstrate thoroughness. Finally, emphasize the importance of analyzing time complexity. Interviewers frequently expect you to identify and optimize the solution, mentioning n, or even log n methods when applicable. The climbing stairs problem also connects to several related problems that share similar principles. For instance, LeetCode 746, min-cost climbing stairs, introduces costs for each step, requiring you to modify the recurrence relation to account for these costs. Then there's the base problem, climbing stairs, which you should master before tackling variations. Another related problem is LeetCode 198, house robber, which involves dynamic programming but with an alternate recurrence relation. Finally, LeetCode 1137, nth Fibonacci number, extends the Fibonacci sequence to 3 terms instead of 2. Solving these problems helps build a deeper understanding of recurrence relations and dynamic programming techniques. Now let's look at some alternative approaches and their trade-offs. The recursive approach without memoization is the simplest to write but is highly inefficient, with 2 to the power of n time complexity due to redundant calculations. Adding memoization drastically improves efficiency, reducing the time complexity to n. However, it requires n space to store the cache. Iterative dynamic programming is another option, where you fill a DP array iteratively. This approach is simple and intuitive, but it uses n space for the array. To optimize further, you can use a space-optimized iterative DP solution, which reduces memory usage to 1 by only storing the last 2 values. While this is the most memory-efficient method, proper handling of the rolling variables is crucial to maintain correctness. Finally, matrix exponentiation is another advanced approach for solving this problem. It leverages matrix multiplication to calculate the result in log n time. This method is faster for very large inputs but is more complex to implement and understand compared to dynamic programming. It's also rarely required in interviews unless you are explicitly prompted to use it. While it's important to be aware of this approach, focusing on simpler, more common solutions like iterative or space-optimized DP is often sufficient for most interview scenarios. Great job on making it to the end. Today, we explored the climbing stairs problem, a classic example of dynamic programming. Remember the importance of optimizing both time and space complexity and how these concepts apply to a wide range of problems. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you in the next lesson. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!